Hi everyone, my name is Cha and welcome back to my channel. Today I'm going to be talking about analytical chemistry techniques for the MCAT. This is super important. You'll probably get at least one question about an analytical chemistry technique, and they're often integrated into the articles that you read for the MCAT. So it's understanding like just some background on what the heck is actually happening when you read a passage, since it could be kind of confusing. And if you see something that's familiar, it might help you just like be like, oh, yeah, I totally know what this is, since it could be nerve-wracking when you actually take the test. Um, so I'm gonna first be talking about the blotting techniques. Oh, also, I'm not gonna talk about gas techniques during this video, just because I realize that I have a lot going over and I don't want this video to be an hour long, so that'll be a separate video. So first I'm going to be talking about the blotting techniques. So Southern blotting, hence the name, it was created by Edward Southern, which is a great, fantastic even last name. But so how you can kind of remember Southern blotting versus Northern and Western blotting, like what it is, since like Southern is for DNA, and like DNA, it's like Southern blotting is like the first blotting technique, and DNA is obviously the first part of the central dogma. So like that's kind of how I like to remember Southern blotting versus the other two. Um, like all the other blotting types, you're basically comparing the size or molecular weight of that particular strain of DNA, or like the of that molecule. So it's like for northern, it'll be for RNA, and Western, it'll be for that protein. But we'll get more into that for STS page. So small compounds are easier to move, right? So it just kind of goes back to like inertia for like physics, right? If you have something that weighs 500 pounds, like this little guy, he's like really struggling. Um, it's impressive that he was even to move, able to move this like 10 feet, right? Like that's like the maximum that he can push. Whereas this guy, he's like Speedy Gonzalez with his three little lines that are his wind, right? He's like moving, so he can go 100 feet with the 20-pound like block. It's much easier for him to go. That's kind of the same thing, right? Um, when you do like gel electrophoresis, because like molecular weight is like a lot harder for them to move downstream just because it requires more force, more energy. And also all DNA is negatively charged because of that phosphate backbone. For example, this is a picture of adenine. And then here's that phosphate backbone, it's that negative charge. So going off of that, because DNA is negatively charged, right? So when you're looking at it through the lens of like electricity, just like magnetism, um, negative like repels each other. So like that negative field that doesn't like each other. So the DNA will want to go towards the positive end of the gel electrophoresis, since when you put it inside like the little machine, and if you run it, you see a bunch of like bubbles. I don't know if anyone's ever done it before, but I've run many of these, and it's pretty easy. But anyways, there's like small little bubbles, and it generates a small electric field. So when you load your compounds into the agarose shell, which is typically what it is, and then you also have a solvent too, which helps magnify or helps move the electricity or the magnetic field like into the compounds and moves it towards the positive end, like disperses the charge, sort of like a metal does, I guess. But I'm rambling. But so like you have the positive end towards this side, so like the negatively charged DNA is going to want to go towards the positive end, right? Because it's opposites attract, whereas like repels. So it wants to get as far away from that negative charge as possible. Um, so this is like a larger compound. So like larger compounds, as we said before, right? Like they aren't able to move as far down because it takes a lot more energy, a lot more force in order to move it further down. Um, and whereas small molecules, they can go really fast. And also usually you'll see like a DNA ladder on the side, and that's just more or less a frame of reference. So it's going to be the same each time that you use a gel. It should be around the same. So like let's say this is like 10,000 kBs, and down here it's like 500. Um And then in order to see your results, you can expose it to an X-ray or some other fluorescence, depending on what your tag is that you used. So northern blotting. So this is the one that's focusing on RNA. How I like to remember northern versus western blotting is that northern is kind of the opposite, or sorry, north is the opposite of south, right? And I feel like DNA and RNA, they're sort of opposites. Like when you look at the grand scheme of things, like DNA is for transcription, RNA or mRNA. This is specifically northern blotting is usually for mRNA, instead of like tRNA or any of the other types. That's also an important distinction, is because like RNA is kind of like the opposite. It's for translation. It's like the next stage. That's sort of how I like to think about it. But if you have any other like preferences, techniques that help you remember northern, southern, western blotting, feel free to put it in the comments. And then all RNA, like DNA, right? Like since the only thing that's different is like that OH group, right? For RNA, so it's negatively charged since it still has that phosphate backbone. Same thing, you're gonna use gel electrophoresis for this. You have the ladder, large and small, like repels each other, so like that negatively charged wants to get as far away as possible, whereas you have a positive charge down here that it's attracted to, and it generates a small electric field. Um, in order to like realize like, hey, like what RNA is this, you can insert a probe with like complementary sequences, which can be like DNA or RNA, for like an oligonucleotide probe. So it's or you could have like a cDNA probe for which is like obviously going to be DNA, so it's just a complementary DNA. So it's like it'll bind to each other, and then you could have the same thing, so radioactive labeling, or you could have fluorescence as well, in order to see, hey, like this is what's happening. And then Western blotting, I don't really have like mnemonic for this, like to like how to memorize like Western. It's just kind of like the odd man out. Like I feel like proteins are not really like the other, I mean they are, it's like the final stage of it, I guess. Of like the central dogma, I guess. And like I feel like West isn't like North or South. So just kind of like the odd man out. So instead of using a gel electrophoresis, like the other two, you're gonna use an STS page, which is more or less the same thing. So in an STS page, you're gonna denature the proteins. And then a lot of the times you'll make sure, since sometimes in the MCAT, like read the question really closely, since sometimes it'll say you're adding a reducing agent to break apart the disulfide bonds, which typically it's like something called DTT. But a lot of the times, like you don't need to like memorize like that is CTT or any of the other reducing agents that are commonly used for STS pages. But do read the question carefully, since sometimes it says it won't. So that can also be like a distinction. So it can tell you, hey, like there's some like cysteine residues or like there's some disulfide bonds that are getting broken up. Um, and then this is also a callback to the amino acid cysteine, since cysteine is the only amino acid because it has that SH group, has that SH group, um, that can form, like disulfide bonds. So that's why cysteine is like really important, amino acid. Yeah, here, so like, yeah, it's not great. Oh my gosh, here, let me draw this better. Yeah, C, H, let me sort of boom, boom. That's cysteine. Um, and then also like you can add a reagent or to make sure that there is a uniform negative charge across all the proteins, because like the other two like electrophoresis for Western and Northern blotting, I'm not Western, sorry, Southern and Northern blotting, you're using size selection for your STS page. But the only difference too when you look at that STS page, is that like you could have multiple bands within the same like column. So like when you load up everything, all of your compounds, like you could have multiple, since it's like separating since like SCS pages and like Western blotting itself, when you denature the proteins, there can be a lot of different proteins that are inside each of your um oh my gosh, sorry, like little vials of interest, like your little here. loading of interest, I guess. So yeah, it's the same thing. So like repels each other, opposite attracts. So like the larger your protein is, the less down the page it will travel. Also another distinction too is that you could have a large band like in an STS page that often can signify, hey, there may be more protein here than there is in like a different one. So like if you see something that's like thicker, like um that, there's probably more of that protein in your STS page. Um, and then a lot of the times after you do an STS page, you can isolate the your protein of interest by using antibodies, because that's what proteins will bind to, is those specific antibodies. That's kind of all I have on STS page. Oh, excuse me, I don't know what the heck. Okay, so now I'm gonna go more, we're gonna change gears since that's kind of all I have to say on bonding. We're gonna talk about size exclusion chromatography. So I like to think of size exclusion like where's my ways? Like it's like for the small ones, because they can just go through, they could do like, like the Bella Hadid meme where she just like, where's my waist, Bella Hadid? It's like she could just like pass through the beads since she has such a small waist. It won't get trapped in between the beads. So small proteins can go past. Large proteins, they take longer elution times because they can't move past these resin beads because they are too thick. So like this is a small protein, right? She's moving in and out. She's going left to right, side to side, shaking her waist like Shakira. And then the large proteins, right? They're like this highlighter. Like, oh, they got trapped. They can't go past any further. They have to do some more fine maneuvering before it can actually go through. Size exclusion too, it's like obviously like it just separates on size, so it's not very like specific, I guess. Then you have affinity-based chromatography. I like to think of this as like a jack of all trades, kind of like the other of the chromatography. Like there's like not really too much to like to distinguish it by, but it's really, really, really specific. So like if you're like, for example, like if you're looking at histidine, trying to separate it from nickel, resin and beads, then it's a great way to sort out impurities. Um, yeah, it separates molecules based on like how well they bind to the ligand, right? So if like you have that nickel resin bead, you have histidine, and a lot of times you'll use correct me if I'm wrong, I always like have trouble like pronouncing the names of molecules. Imidazole? Imidazole? Okay, I'm just gonna call it this one. So basically similar structures and impurities are removed with like low concentrations of your imidazole. Um, and then at high concentrations, right? Because like histidine at low concentrations can like outcompete the imidazole because like there's not a lot of it that can bind to nickel since like imidazole, oh my God, I can't, I'm sorry. It has a stronger affinity for that nickel. So like at low concentrations, it's not pushing the histidine out yet. Histidine can still bind to it. So like at low concentrations, it's actually really great since it can get rid of like the imposters that are like sort of bound to the nickel, but like not really. Whereas like at higher concentrations, eventually the histidine will get booted off of the nickel because it can't really bind as well as the imidazole. So since it outcompetes histidine, and then histidine is slowly eluted out. So it's a great way to get rid of the impurities for certain molecules and proteins. Hmm. Um, then oh, excuse me, I'm just getting a water. Then for cation exchange chromatography. So like the name suggests, so to be kind of, at least for me, when I was first learning this, it was kind of confusing. Like, what is the cation? Like, is it talking about the resin, like the beads that your proteins are attracted to, or is it talking about the proteins itself that are the cation? So it is always for cation and anion, you're talking about the protein itself, the molecule itself. That is what's positively charged. Whereas the resin and beads, those are what are negatively charged. So the more positively charged proteins, they'll form a stronger bond than those that have a weak negative, sorry, positive charge. which makes sense, right? Since like opposites attract when you're talking about electricity and magnetism. So, for elution, in order to like get rid of like those positively charged proteins, in order to elute it out, a solution is just like going through like to collect it. You could increase the salt concentration since like Na plus, because it's a small positively charged molecule, it'll outcompete like a lot of the other larger and like I guess like the bigger and like they since they have a smaller z score, since like molecular weight, z is equal to molecular weight over charge. So like obviously sodium, it has a very small molecular weight, but it's like positively charged. So it'll outcompete a lot of those proteins or in molecules. Or you could also increase the pH. So when you increase the pH, you're increasing the hydroxide concentration, while also simultaneously decreasing the H plus concentration or proton concentration. So like when you increase the hydroxide concentration, you're deprotonating the positively charged molecules. It's like OH, it's a super strong base, right? So it really, really, really wants to collect the hydrogens um from just like different molecules, and right, because like if a compound is like positively charged, it wants to get rid of that positive charge. It's better at like handling the charge than like a lot of other molecules, but still it's like not that great. Like everything wants to be neutral. Neutral is like the ideal. It's like it's trend of for proteins and molecules. Um, so like the OH minus, like the hydroxy group, it'll deprotonate those proteins, making them neutral. So when something is neutral, it can't bind to a negative charge, right? Like it's a lot more weak. So it's not likely to bind to the resin. When your pH is less than your PI, your protein is positively charged. Due to it being protonated, right? Since like it has like more of like the hydroxide, I mean, sorry, proton concentration. And then so like how I like to remember this too, if like you're kind of like confused with like the whole pH and PI thing. I always like thinking about like lysine or arginine. So like lysine has a pK of 10.5 approximately, and arginine is around 12. So they're protonated and they're charged at pH 7, right? Like just think of those molecules, since like they have a higher pKa, which is like you could sort of be if it's like literally only like lysine, like the pi and pKa are synonymous with each other. But obviously if you have more proteins and molecules, then that's not true. So like in this case it is so like that pi is greater than that pH 7. And lysine is positively charged, right? So like that's how I like to think about it. Um And then for anion exchange chromatography, so proteins are anions. They're negatively charged, right? Since it's like the anion is specific to the protein itself, not the resin. The resin beads are positively charged. So the more negatively charged proteins, they form a stronger bond. It's like the exact same thing as the cation. This is just kind of like the antithesis. It's like the opposite of it. Bizarre world of the cation exchange chromatography. Um, and then the elution is the same thing. So like if you increase the salt concentration, you have your chlorine, it's gonna outcompete because like chlorine, same thing, like it has that negative charge and it's a small molecular weight. Um, which is your Z. Same thing, if you decrease the pH, you're increasing the proton concentration, right? So you're gonna protonate the negatively charged molecules, like those are gonna act as a base, right? So like they have excess electrons, so they're able to take in those hydrogens. And as I said before, it wants to be neutral. Like no compound wants to be positively or negatively charged. It's like high energy, and it's just not great, just overall. So it's not likely to bind to the resin when it's neutral. Same thing, pH greater than pi, the protein is negatively charged due to being deprotonated. And then, like, if you're confused again, I like to think of like aspartic acid or glutamic acid, aspartic acid with its pK of 3.8, or if it's only like protein, like amino acid residue, then it's synonymous with the PI, and same thing with glutamic acid with its pK or PI in this case of 4.2 approximately. So it'll be deprotonated, and it has a negative charge of pH 7 because its PI is less than 7. So that makes sense. And also, this don't feel bad if it takes you a while. I still sometimes get like tripped up with this, and I've been like trying, attempting to like do this stuff for like 2 years now. So it's can be complicated. It's just like a matter of fact of like thinking through it logically, and then especially like if you're under pressure, it's really good just like have this like snap of your finger, super quick. Since this, they do like to test on like like pH and like PI and that type of stuff. So like sort of have that down. And think know how to think about it logically too. And having those examples of lysine, aspartic acid, and glutamic acid, those are great. Okay, now I'm gonna switch gears again. Now we're gonna talk about like TLC, which is thin layer chromatography. Um, so in TLC, you have a stationary phase. So the base, I don't know what it's called. I call it the base. So like what you load your samples on, it's polar. So it's typically gonna be like silica, cellulose, or aluminum. Um, like either a lot of times, like if you've ever done like organic chemistry lab, like you'll like put here, I have like a little, I chose this. I like took this off the internet, but you'll have like a little tiny like almost piece of paper if you will. And then you'll like put in a solvent, and then like through the power of like osmosis, it'll like just travel upward, like the solvent will just go up and it'll bring along the what you loaded onto the TLC plate. It'll bring up the substance with it. So that's kind of an example of it. And then the mobile phase is non-polar. So it's a solvent that you add into your TLC plate, like onto that little experimental like beaker. And then substances that are polar interact strongly with the stationary and polar phase. So they're unlikely to move up. So like this is like kind of tricky, right? Since like with electricity and magnetism, likes repel each other and then opposites attract. But this is the opposite for like when you're talking about like solvents and just like hydrophilic and hydrophobic substances. So like likes dissolve and attract likes. So it's like if you think of like that oil and water example, right? So it's like water, it's obviously hydrophilic, hence the name hydro, water, philic, loving. And then oil is hydrophobic, so water phobic, like hatred or like afraid of. So it's the same thing. So like just sort of like if you're getting confused about that, just like think about like the water and oil example. And then the opposite is true for nonpolar. So if you have a nonpolar substance, it's likely to travel, right? Since it's like it doesn't like the mobile sorry, the stationary phase. It doesn't like that silica gel. So it wants to get as far away from it as possible, right? It's like running from its problems away. And then you have your RF, which is like the total distance traveled by the compound slash substance. And then the distance traveled by solvent. So it doesn't matter how far the solvent or the compound go. It can like go infinitely. It's just like a ratio of this. And it's always going to be less than one. That's like another thing. If they like try and trick you and they have an answer for like 1.4, like that's literally impossible. Like the compound can't travel as like further than the solvent because like the solvent is just like how it moves up the plate. Um, so then we have UV spectrometry. So it UV, right? Since you have like UV visible infrared spectrometry. Oh no, sorry, wavelengths. So it works in low wavelengths. So around approximately, I like to say just 250 since that's like applicable for the MCAT, around 250-ish nanometers. And then it's important for aromatic and pi bonds. So sp2 hybridized molecules. So it absorbs energy and it transitions to like the higher levels of the energy. Just like that's like gonna be a common theme for like when we move into like the spectrometry stuff that's that it's like just absorbing energy and like exciting said compounds. And then for the MCAT, the three molecules that we really care about for like UV spec is phenylalanine, tyrosine, and tryptophan. Those are the big three, since those are our aromatic amino acid compounds. So I would really memorize that. So like if you have something that's like, oh, like cysteine, like does that like UV spec? No, because it's not aromatic. Like just like think about it logically. Like if you see something that's sp2 hybridized, it's probably gonna be important for UV spec. But if it's not, we don't care. Like it's not gonna show up. And then you have IRspec. So it detects functional groups, whereas this is more or less like electrons and excitation. This is for functional groups and for covalent bond excitation for the dipole moment. So it's looking for like most of the time it's primarily for covalent bonds. So it's looking for like the shared electron pairs and that dipole moment. And it is looking at for bond vibration. So it's looking for like different dipole moments. So it's like the molecule like moving back and forth. So it kind of has like the zoomies, right? Like when you see a dog just go boop boop boop, like super fast back and forth. Um, and then like here's an example of it. So we have that fingerprint region, which is over here, which is typically give or take, some scientists have different like ideas of what the fingerprint region is, but give or it's a pretty good guess if it's less than 1500 centimeters. Right, so -1 power, it's going to be a fingerprint region. So it's going to be like you need a computer like humans themselves just because like the peaks are so close together and there's just such little variance in that region. You need a computer or like some AI in order to do it yourself. Or maybe if you really, really care about chemistry, then you could take analytical chem or like some higher level like class and they can tell you how. But also the fingerprint region just like is not really important just because like these are like where there's like super like the electronegativities of the pair seats like you could see like the CC carbon carbon there's like they're like the same thing. It's like there's not really much excitation because the electronegativities are so similar. Ah, yeah, and then so here are some that I think like are really important for the MCAT that you need to have memorized. Like when you look at IR graph, you could just like tell. So you need to know like OH bonds. So OH and NH bonds, they're both around 3,300 centimeters, so raise -1 power. But the only difference is that OH bonds are wide, so like they have like a really wide peak, and then NH bonds are narrow. And then the carbonyl, so like a carbonyl is here, so it has a C, double bond is to oxygen, and that's typically around 1,750 centimeters, so -1 power. Oh my God, please don't fail me now. I have one last thing. Okay, woo, we're almost done. Let's go, guys. Um, then we have nuclear magnetic resonance or NMR. This is I've I like in organic chemistry, this was literally like the bane of my existence. And now, like in the lab that I work at, sometimes I have to do NMR myself, and I still hate NMR. Like this will forever be like one of my least favorite things that I have to do. So basically, you use magnetic fields to analyze molecules. So like, there's a couple of different neuroimaging things that you'll see like in the psych section, and it's just cool kind of to know. So fMRI, which is like uses like blood or like it uses like water which is like a polar molecule, right? Um, and it looks at like the de-shielding of like those different, it looks at like de-shielding, it's just like a practical application of it. It's like the same thing, but that's just more or less. And then MRI is more, those are both fMRI and MRI. They're really good at spatial, like looking at things in like space, like having like, oh, like this is like totally what like this is what the brain region is activated by. Whereas like if you have an EEG, which is more like really it has like really good spatial not spatial, sorry, temporal validity. It's like really good with like in time. So it's like super fast. So if you think about it, like I'm getting like off track right now. But if you think about like blood, right? If you're tracking blood versus like an electrical signal, like blood flow to your brain, it usually takes like a couple seconds. Whereas if you have like a synapse firing, that's like a millisecond. So very different, but NMR is really good for like that spatial validity. Anyways, de-shielding. So there's like three main points of like NMR that you should know for the MCAT. It's not super important, at least in my opinion, to like know. It's kind of wasted time to like remember like where all the peaks are, but knock yourself out if you want to. I'm not gonna like talk about that in this. So de-shielding. It's when your hydrogen. So also we're talking about like hydrogen NMR too. We're not gonna talk about like carbon NMRs. That's like rare even in like organic chemistry classes to like really care about that. At least in my experience. Is the hydrogen Sorry, de-shielding is the hydrogen close by other atoms that have a significantly different electronegativity. So like are those atoms pulling the electrons towards themselves? And if so, typically it'll be like further downstream. So like it'll be like I don't know, like 10 or like 12, like it'll be like further downstream as they are exposed to the magnetic field, right? So like here, for example, you have this methyl group. Um, and it's not by any like just assume I guess like this could be like a carbon. So like when it has a carbon-carbon bond, right? Those electronegativities, since carbon and carbon, they're the same thing. So it's like pretty negligible. Whereas if you have this like aldehyde group over here, right? Like this is next to like a really, really electronegative oxygen. So like it's pulling those electrons away from the carbon. And that hydrogen is really de-shielded. So it's really, really susceptible to that magnetic field. So it'll be further downstream. Um, and then integration, as the name suggests, it's just like how many total hydrogens have the same like fingerprint or like how many are identical. So for example, like if you have CH3, like yeah, there's like three hydrogens that are bonded to carbon, but each of those hydrogens are they're the same, they're identical. Since they're bonded to the same atom, like they have like if this carbon was like next to like a CH2, for example, like it has the same neighbor. So all of those are considered like chemically identical. They have the same fingerprint. Like if they were criminals, right? Like they're like it's really hard to like distinguish between the two, like using like a fingerprint because they're the same. It's like even though like one of them committed the crime, like you don't know which one because there's nothing to distinguish them apart. Um, yeah, and then you have like coupling, which is like how many neighboring hydrogens are there? Um, sorry, coupling. So how many neighboring hydrogens are there? You need to make sure to consider each equivalent hydrogen as one neighbor. So that's really important. So like if your neighbor was like CH2, those are not, you don't have two neighbors, you only have one neighbor. And then so like there's also a rule for this, so like it's the n+1 rule. So essentially why is n+1? So like n is just like how many neighboring hydrogens you have, and then you add one. So like if you have we'll get into it, I guess, like since I haven't further down. But assume that like the hydrogen, like why is n+1 rule? So like assume that if you have a hydrogen, you always need to have a peak, like even if it doesn't have a neighbor. Otherwise, like how do you know it exists, right? Since like if you have a single peak and no neighbors, it's a singlet. Like it's not just gonna have like a zero peak. Like since otherwise, like if you're looking at a graph and you just like see like, oh yeah, like there's like something like here, right? Like at 8, for example. Um, yeah, it's a singlet. Or like that's why you would know that like the integration is like 1. But or not integration, but that's how you would know that there's a peak there. Otherwise, like if you're looking at a graph and it's like, oh yeah, there's like totally something at 8, but like it just doesn't have any neighbors, so we just put 0 there. Like, no, you can't just tell by quick glance. That's not how that works. And then if you have a doublet, um, that means that you have one distinct neighbor. So for example, let's look at like this hydrogen on the aldehyde again. Um, if you can see, it's next to that carbon and it has three hydrogens there, but each of those hydrogens are the same. Like they're exactly the same, like fingerprints the same. Um, so it's technically one neighbor, so it's a doublet. So it's n+1. So as one neighbor plus one is 2, so doublet. And then really all you need to know up for LAMCAT is like up to triplet. Other than that, Like you don't care. Also, yeah, so this is like what a singlet will look like. This is a doublet, and a triplet will look like that. If you're looking at a graph. And then for a triplet, you have two distinct neighbors. So for example, again, we're looking at this. Um, and then up here, let's look at this guy here, right? So it has one neighbor here, this is unique, and then the CH2 group, right? Since like each of these two hydrogens are identical, so that's one neighbor. So this is another neighbor. So that's two neighbors. Ah, why'd that go away? I don't know. So it's a triplet. Hopefully that made sense. NMR can be a little tricky, but I feel like these are like, it's just like kind of like the basic things that you need to know. If you have a really good foundation of the basics, then everything else should fall easily. Then a lot of the time when you're like looking at an NMR graph, you could kind of distinguish like where something should be, right? Since like if you're looking at like this aldehyde, obviously that's going to be a lot further down than like this methyl group. So just like think about it logically, like how electronegative. Also, the other thing too is like if you have like something that's aromatic, that is also going to be like pretty deshielded. Double bonds are more deshielded compared to single bonds too. So just like think about it logically like that. That's like the other thing that I guess is important. Well, hopefully this made sense. These topics can be kind of tricky, and it's okay if you need help. Don't, yeah, don't hesitate to like try your best. But, yeah, good luck.